So they specifically say that, calculate the electric field at a distance small r from the center. So they kind of tell you what this variable is, what the radius you need for the Gaussian surface is. But if you do that, then you're going to have this trouble. So let me show you what trouble I'm trying to avoid. So let's say that then I integrate from 0 to r, if this is the radius of my Gaussian surface, and I want to try to get the charge inside. And to get the charge inside, I'll multiply by the density and by dV, but these are also given in terms of r. So from 0 to r, alpha r squared, 4 pi r squared dr. And so this is the rho, this is the dV. Now, this is very confusing because the limit of your integral is the same as your integration variable. Yeah. And, there is a way to handle these formally, but this is just slope notation. So you just change this. Okay. That's what I did. So when I write this definite integral, it's not going to be in terms of small r anymore, but the limits of the integral. So it's not clear what small r stands for if you just use small r for two things. That's why I changed it. So I thought I was avoiding confusion, but apparently it led to more confusion. Was there a question? Is there anything further based on this? Okay. Are there any other questions with what we covered in the previous session? Okay.
Hocam şimdi bu bigger r sphere'ın radyusu, doğru mu?
So these are all spheres. Okay.
No,
the Gaussian surface is a sphere. The charge distribution is a sphere.
One of them, the Gaussian surface, I know. The other sphere. I mean, the bigger r is
the charge distribution, the solid sphere that contains the charge has radius r0.
Okay.
But if you're looking at the situation where we are inside the sphere, which is given by this, then r0 never enters our equation, except through q. Right? Q includes the q inside includes this r0. Any other questions? Okay, then I'm going to take a look at this question sent to me. Can you see it? Is it all?
Yes, yes.
Okay. Now we have an insulating sphere of radius a, and centered at the origin, and has uniform volume charge density rho. Right? Then we carve out a spherical cavity, or we excise the spherical cavity from inside the sphere. The cavity has radius a/4 and is centered at position h vector, where the magnitude of this vector is less than 3/4 of a. This ensures that the cavity is entirely contained within the larger sphere. And so this is h. They're choosing this h along the x-axis, but this can be done without any loss of generality. It can be in any direction. They're asking us to find the electric field inside the cavity. And they're saying express your answer as a vector in terms of any of all rho, epsilon naught, r vector, and h vector. And this is, I believe, the answer. Okay, well, let's try to find this out. Is the question clear? We have a spherical cavity, and we excise a little sphere inside this. And we have to find the electric field inside this cavity that we just created. And it's uniform, they're giving us the volume charge density to be uniform of value rho. Is the question clear? Because I'm going to stop sharing to show you the whiteboard. Okay. All right. Let's erase this. Now I'm going to use some results from the previous parts. You could, of course, completely rewrite them, but that would be a waste of time at this point. So I have a sphere. Oh man, I'm running out of ink. My purse. Okay. And it's of radius A. And let's say on this axis, some part of this is removed. And this one center is at H. Okay. And they're asking us to find the electric field inside this cavity. That's all right. Is there anything else? No. The cavity has radius A over 4. But this is just, make sure this all falls within the sphere, I believe. And this is some charge density, rho. So first of all, can we use Gauss's law for this problem? And Gauss's law, as I keep saying, requires a high degree of symmetry. Does this problem meet that condition? So it has cylindrical symmetry around some rotational symmetry around this axis, okay? But it certainly doesn't have rotational symmetry around every axis. It doesn't have spherical symmetry. And yet, this is apparently a homework problem from this chapter. So what do we do? I mean, can I draw a Gaussian surface around here, or perhaps inside, and try to calculate the electric field that way? That would not work. Why will it not work? Why would this fail? Because on that surface, there is no guarantee that the electric field is going to have a simple relationship with the normal vectors, right? So these will be my normal vectors if I draw something like that. And electric field could be any which way. You just don't know. You can't say it's going to be in the radial direction, or you can't say it's going to be in the transverse direction or anything like that. There's no symmetry here, right? The charge distribution outside is not spherical symmetric. It's not going to produce a spherical symmetric electric field inside. It produces something simple, as we'll see in the end, but you can't use Gauss's law directly, blindly. So what do you do? What's the secret keyword? What's your superpower?
Hocam, I tried to solve this question when there's a cavity, and I just imagined it was in the middle, maybe calculated that, so I can just fit it into a symmetric position, so it will be maybe easier.
If it was at the center, then yes, this would actually reduce to the other problem you sent me. So then it will be simpler, but it's not. So what do you do? Now we covered this already. It's very easy to forget, but there's a way to attack these kind of problems. Like, for example, Coulomb's law for a point charge, right? In fact, Coulomb's law is generally given for a point charge. Now, what do you do if you have 2 point charges? What's the strategy? Let's say that you have 2 point charges and you want to calculate the electric field. You already did this. You want to calculate the electric field somewhere in space. What do? You calculate the electric field from this charge, then you calculate the electric field from this charge, and you add them up. That's superposition. Now it could work here. How will it work? We're going to imagine that this sphere with cavity is in fact 2 charge distributions superposed on each other. Something that's complete with rho, and another sphere that has negative rho. When you put these together, in the location of the smaller sphere, the charges are going to cancel, you get 0 charge. And outside the small sphere, inside the big one, you're going to have just rho. Okay?
Hocam son dediğinizi tekrar edebilir misiniz hocam?
Yes. So, first let me go back. I'm going to imagine this situation, instead of having something with rho with 0 in the cavity, I'm going to say there is rho everywhere, including the cavity. So I have a uniformly charged sphere with charge density rho. On top of that, I'm going to have a charge sphere at the location of the cavity with charge density negative rho. And then in the cavity, that negative rho is going to cancel the rho of the original full charge. And I'm going to end up with 0 charge here, 0 charge density here, and rho charge density everywhere else. This is, in fact, what happens inside a neutral conductor. And conductor does have charge. Right? It has negative and positive charges. They just cancel each other out, so you don't see their effects. You don't say that, there's some negative charge and positive. It's charge neutral, but charge neutral means that there's equal amount of positive and negative charges. So you can imagine it this way. Instead of saying there is no charge here, just imagine there's some sphere with positive rho and some sphere with negative rho. So they're going to cancel over here. And of course, they're not going to cancel over here at all. So rho is going to remain here. Okay? And these are not conductors. These are, this is insulator. So the charge doesn't just move around to cancel the electric fields and things like that. Does that make sense? So instead of this, I'm going to assume 2 charge distributions. And imagine this is negative and this is positive. So they cancel out here. There's no charge over there, and there's some remaining positive charge on the outside. And they have the same magnitudes of charge density, except this is negative and that's positive. This is the situation I have in mind, and this allows me to solve the problem with the results from Gauss's law, because now I have 2 charge distributions, and for both of them, I know what the electric field is going to be. I already calculated this. I already calculated the electric field for a solid sphere with uniform charge density. Do you agree? Is there anyone who disagrees or is still confused as to what I'm doing here? Okay, so how did I figure this out? How did I come up with this crazy idea? I've seen this before. Right? In fact, I've seen this 30 years ago when I was a student in your place. And you see enough problems like this, and you see something like that, you say, oh, I have to use position, so I can actually end up with some charge distribution that I know the electric field for. But let's solve this problem using superposition. So from Gauss's law, we already calculated the electric field of a solid sphere of charge, and that was inside. On the inside, it was proportional to R. Right? So let me just copy what we had before. E was 1/4 pi epsilon naught Q over R naught Q times R. That's in the radial direction. This is for a sphere of uniform charge density carrying a total charge Q. Now they are giving us rho here, so I want to convert this to something in terms of rho. Okay? But that's easily done. So I just need to come up with some volume and divide this total charge into volume. And to turn this into a volume, I'm going to divide this by 3 and multiply it by 3. Okay, so this is going to be Q by 4 pi 3 R0 cubed times 3 epsilon naught times R. Yeah. So I divide by 3, I multiply by 3. But now this is just the total charge divided by the total volume, it's just rho. And R is wherever you are in the sphere. Okay? So if you're at this point, your R is going to look like this. If you're at this point, your R is going to look like this. Okay? And everywhere, it's going to be in the direction of this R, and it's proportional to the magnitude of this R. Are you with me so far? So now I expressed the electric field I found before in terms of rho, and I'm going to use the vector property of the electric field, because I'm going to, inside this cavity, I'm going to add the electric field coming from the positive rho big sphere and the negative rho small sphere. I'm going to add the contributions from these two, and they're going to have different directions. Right now, let's say that. Let me erase this because I'm going to draw some vectors here. Put this up. Right, I'm going to keep my H vector over here. Let's say I'm at the point over here. Yeah. And I'm going to call this point capital R. That point, with respect to this little sphere, center is going to, I'm going to call it small r. Okay. Now, the electric field I have is going to be electric field coming from the positive R plus the electric field coming from, sorry, positive rho, and the electric field coming from negative rho. And I can write these. So the electric field coming from the positive rho is going to be rho times my position with respect to the positive rho distribution is just capital R over 3 epsilon. Okay. So at this point, there are two contributions. One coming from the positive charge distribution, the big sphere, it's given by this. And there's going to be a contribution to the electric field coming from the negative charge distribution. That's going to be minus rho, the small r, my position vector with respect to the center of the small sphere, divided by 3 epsilon naught. Okay. And I can take this into common parentheses. This is rho divided by 3 epsilon naught, r minus small r. What is r minus small r? Look at this. H plus r is capital R. So capital R minus r is H. So H divided by 3 epsilon. And that's your answer. So inside this cavity, the electric field is going to be uniform. It's going to look like this everywhere in the direction of H. And of course, now here we put this on the x-axis. There's nothing special about that. If the cavity was over here, it would look parallel to that vector. So the result looks very simple, but the derivation, it's not trivial. Just because the result looks simple doesn't mean deriving it is going to be easy. Any questions on this?
Hocam, I'm still stuck in the fact that the minus and the plus, like how did we decide on that?
Good. It's excellent that you know where you're stuck. Now, so first of all, do you agree with this? So I have, just imagine that instead of these being on top of each other, I have a big sphere of density rho, charge density rho, and I can calculate the electric field for this. And then just forget the big sphere. I have a small sphere located at some position, its center is at some position H with respect to origin. The other one was center was at the origin. This one, its center is off origin by some vector H. And this has negative rho, charge density. And I can also calculate the electric field inside this. Do we agree on this?
Yeah, I do, but I just couldn't understand why negative or why not positive? How did we decide on that?
Okay. Now, what I want to do is to end up with a charge distribution that in a portion of space that is zero, there is no charge. It's charge neutral. The charge density is 0. How do I achieve this? Well, I add to this positive charge density rho some negative charge density rho, some negative rho. If I put these on top of each other, then total charge density in that region is going to be 0.
Oh, okay, I get it now. Thank you.
Okay. And so what I want to do is that, so what did we do for 2-point charges? 1 and 2. So over here, let's say 1 and 2, I calculated the electric field coming from 1, and I added the electric field coming from 2, and this gives me the electric field over here. Now, the same deal here. At this point, the electric field is going to have 2 contributions. I have the full sphere full of positive rho, and that creates some electric field. What kind of electric field does it create? This kind. The electric field produced by a solid sphere inside has magnitude rho divided by 3 epsilon naught times r, your distance from the center of the sphere. This r is distance from the center of that solid sphere. Okay. And it's in direction, it's radial direction. So with respect to this big sphere, that radial vector, position vector, is just capital R. That's what I chose. So it's rho times capital R divided by 3 epsilon. I'm using this result, applying it for this situation. And I'm getting the electric field for the full solid sphere of charge density rho. Now, I also need the second contribution coming from this additional charge. That additional charge is a negative rho density sphere that's located at some distance h. Okay? And I denoted my position, the position at which I'm trying to calculate the electric field, with respect to the center of that sphere, as small r. So now the density is now minus rho. My position with respect to the center of the sphere is given by this r vector divided by 3 epsilon naught. Again, I'm taking this result, applying it to a negative charge distribution centered at this point. Okay? And I add these up. When I add these up, I end up with some vector subtraction plus some common factor. That vector subtraction happens to give the position vector of the center of my negative charge distribution. It's a little bit weird that this is simple like that, but it happens all the time. Some complicated stuff just cancels. And if you try to do this with components, it will be very complicated. You need to do this with vectors. That's why I actually took time to take this formula and turn it into a vector formula. In this form, it will be much less useful. You will calculate the magnitude of the electric field coming from the positive charge distribution here, like that, and the negative charge distribution here, but you won't be able to add those up or subtract those off. But the vectors, it's easy. Perhaps ironically. Any questions or any further questions on this one? I'm happy to spend time. There's something confusing. But if this is the first time you're seeing it, it's not very helpful. Go ahead.
Hocam, could you please briefly explain once again how did we end up with rho times r over 3 epsilon?
So this comes from here. This one we calculated in the previous session, right? Just 1 hour ago. This is the electric field inside the solid sphere of total charge Q and of radius R0. Okay, this was the result that we found. And now here they're not giving you the total charge Q, but they're giving you some charge density rho. So I want to change this into this form that uses rho. But what is rho? Well, rho in this case is just the total charge. If this was a full sphere full of some uniform charge, then this will be Q divided by the volume. And that volume is 4/3 pi R0 cubed. This R0 was the radius that we used in the previous example from the book, example 22-4. So I want to go from this total charge to density. So I want to make it look like this. So I already have Q divided by 4 pi R0 cubed. If I divide this by 3, I multiply this by 3, which I did here. I divide by 3, I multiply by 3. Now this becomes volume. This is the volume of the sphere. This is the charge. The ratio is just a density.
Okay, I get it. Thank you.
Sure. So sometimes you'll be given rho, sometimes you'll be given Q. You need to be able to go up from one to the other. And not just for you, but for everybody, it's not enough that you get it. This is not something you learn by spectating. You need to do this yourselves at home. Go from this, maybe do it for some more complicated geometry, maybe for simpler geometry, but you have to do it on your own. You cannot learn to play basketball by watching NBA. It just doesn't work. You have to take the ball, you have to go to the court, you have to take some shots. Initially, it's going to be painful. It's not going to work, but eventually you'll learn to play basketball. You can't just, watch TV and hope to learn basketball. I wish you could, but you can't. Same thing with physics. I'm not claiming I'm MBA class physicist or problem solver, but that makes things even worse for you. You can't learn to do physics by watching me doing physics. Okay, let's move on to the other problem.
Hocam, we assume that sphere is complete, and we find the electric field inside, but this is not complete. It's not
That's correct.
Wouldn't change the result.
Yes, so we assume that this sphere with cavity is in fact two complete spheres. One with charge density rho, the other with charge density minus rho. So the sphere with the charge density minus rho is a smaller one, situated at this location, and its location, positive rho cancels minus rho. So there are two spheres here, two complete spheres here, not just one. And so I calculate the electric field from two complete spheres, one with charge density positive rho, the other with charge density negative rho.
Okay.
And my position of interest with respect to the charge density with positive rho is capital R, this vector drawn here. And the position with respect to the center of the charge sphere with negative R, negative rho is small r, drawn here. And that is what goes into this formula there. Right? This formula is the electric field for a solid sphere of uniform charge density rho, the electric field inside. And this one is your position vector with respect to the center of that sphere. So this is my position vector with respect to the center of the big one with positive rho. This one is my position vector with respect to the center of the small one with negative rho. So I write this formula twice and I add it up.
Thank you, hocam.
Anything else? So let me try to find the other problem. Yeah. So here, there's something missing. Let me again try to share this. Yeah. So here we have I think hollowed out sphere. So this sphere has two radii. There's an outer radii R0 and inner radii R1. So it's like a thick spherical shell. And we need the charge density function in between these two. So inside presumably it's 0, but you need the function in between. And then you're required to determine the electric field, the function of R in between these two inner and outer radii. So, Gökçen, what is the formula given here?
Hocam şimdi bakıyorum. Hemen size atacağım.
No, don't email me. Just tell me what it is. If you email me, I need to go back to my email client and so on.
No. I'm looking at it right now. So rho E is equal to rho naught times R1 over R.
Something like this. Yeah. Is that correct? R1 over R. Rho naught times R1 over R. Oh, you can't see it. I wrote it on the whiteboard. But anyway, so we have some non-uniform charge distribution inside the sphere or spherical shell. And it has two radii, and they're asking for electric field over here. So let's try to attack this. And I'm told that the density is given by this formula. Let's erase this. Let's see if we can come up with. So I have an inner radius and outer radius. This one is R1, this one is R0, and there's some charge distribution over here that's given by some R0, a constant, times R1, and another constant, the inner radius, divided by R. Okay? And we have to find the electric field as a function of distance, okay? Where R is between R1 and R0. Now, this one screams at you Gauss law, because the density is given as a function of radius only, which means it's spherical symmetric. And spherical symmetric distributions are most easily handled by Gauss law. Now, the Gaussian surface that you need to draw here, of course, passes through the point that you're interested in. Okay? And when you write Gauss law, what you end up with is electric field is going to be Q inside divided by 4 pi epsilon naught R squared. Okay. Again, Newton's theorem from gravity. Any spherical charge distribution is going to act like a point charge at its center to outside. And the outside spherical charge distribution has no contribution to the electric field. So here again, your task is in fact to calculate the total charge from your inner radius to the radius you're interested in. Okay. Again, to make this hopefully less confusing, I'm going to turn this into capital R. So that is the surface, the radius of my Gaussian surface. And this changes accordingly. Later on, I'm going to change it to R because they're explicitly telling you that is in fact R. So what is the charge, the Q inside? Well, we did this already. So from 0 to R1, there's no charge. There's nothing. Okay, so it's 0. So I need to take this integral of my density times the infinitesimal volume integral from simply R1, where the charge density begins, to some capital R. Okay? So this could be something more complicated. That could be different regions with different rho and so on and so forth. Then you would just divide this integral into different parts, where you have a specific formula for the charge density. Now let's write this. So this is going to be from R1 to R. My rho is given to be rho 0, R1 by R. And this dV is the same as what we did before. We are integrating in terms of little spherical shells. So that's going to be 4 pi R squared dr. Now let's rewrite the integral by taking our constants out. So rho 0 is a constant, r1 is a constant, 4 pi is a constant. Rho 0, r1, 4 pi. This r squared gets partially cancelled by the r in the denominator. So this is the integral from r1, capital R, r dr. And this integral can be done. The primitive of that function is r squared by 2. So this one gives rho 0, r1, 4 pi times a half capital R squared minus r1 squared. So that's the charge inside. And you take this and you plug this in. So this is going to be rho 0, r1, 4 pi, a half capital R squared minus r1 squared divided by 4 pi epsilon naught capital R squared. And there are some cancellations, not much, but the 4 pi's cancel. And then you end up with some expression, and you need to turn that into your original variable. You need to turn your capital R into small r, so it's going to be consistent with what's given in the problem. So this one, in fact, becomes rho 0, r1, small r squared by r1 squared over 2 epsilon naught small r squared. Now you make the cancellation plus the substitution for small r for capital R. Okay. So I kind of took a shortcut here, which you are perfectly allowed to do. Okay. So this is the analog of Newton's theorem for gravity for electrostatics. This was derived by Gauss's law. So we already know this. Any spherical charge distribution acts like this. It's going to produce an electric field like a point charge. So this is how the electric field from a point charge looks like. It goes as 1 over r squared. And this is the magnitude of that charge. Okay. Now I need to calculate this magnitude. That is calculated by some integral. Why? Because the charge density is not uniform. Because the charge density is not uniform, I cannot just say it's rho times v. I can just calculate the volume and multiply it by some density. Instead, I need to calculate it for some small infinitesimal volume over which the density is in fact constant. And for that, we choose spherical shells. The volume of those spherical shells is just 4 pi r squared dr. The density, charge density at those shells is given by this formula, rho 0. We multiply these and integrate over. And we only want the charge that's inside. So our limits of integral is from the inner radius, where the charge density begins, to capital R, where we are trying to calculate the electric field, which is the radius of our Gaussian surface. And then it's just algebra. I don't know. Do not trust my algebra. Yeah, I'm pretty confident in what I say about physics, but my algebra, factors of 4, factors of 2, I get confused all the time. Well, I think the algebra is very straightforward here. Of course, it's a particularly simple function. So, any questions about this one?
Hocam kolay soruymuş ya.
Yeah. Well, once you know it, it's easy. But that's exactly the feeling you should get, when you look at these problems. It's a very bad feeling to get after the exam, but it's an excellent feeling to get during the exam. So, like after the exam, you look at the solution and say, "Oh man, they're very easy." That's a bad feeling. But during the exam, if you look at this and you feel like, "Oh, this is easy," that's a good feeling. It happened to me once, and I just so I had failed the course. The only time I failed the course was complex calculus. So I failed the course, and the second time I had to pass it. And I studied like crazy for the final because my first 2 midterms were not guaranteeing that I would pass. And I really for a week, I studied nothing else but complex calculus. So everything looked very, very easy. So in the final, like I, looked at the problem, I just write the answer. This is 2 pi, this is 0, this is 2i, and like 10 minutes, I was done. I said, okay, it can't be this easy. I must have done everything wrong. I erased everything, gave an empty paper, left. Turns out everything I did was in fact correct. I had studied so hard that everything was looking so easy, and I failed again. So I failed a single course, but I failed it twice, and I never passed it. I never passed it. It became an elective after that semester. I took another elective and just forgot about it. Anyway, any questions about this one? So the reason why it looks now easy to get Chen, because she already thought about it. So now she can follow the solution and understand. If it's the first time you're seeing it, it's not so easy. That's why I want you to send me questions, and that's why I want you to look at the examples before coming. So when I saw an example, it's going to be useful. Now I want to, in the last 10 minutes, I want to look at one more example from the book. Enough with this spherical distributions. Let's look at another symmetry. And this is something we have already done before, but using Coulomb's law. The electric field of a long uniform charge. And that one is, again, not too hard, but it can be a little bit confusing. So we have some rod, an infinite rod, so this goes to infinity. It's positively and uniformly charged. So this is linear charge density. It's generally given as lambda, okay, charge per unit length. Let's read this. A very long straight wire possesses a uniform positive charge per unit length lambda. Calculate the electric field at points near but outside the wire, far from the ends. Okay? So they're being very careful. Of course, you can't have an infinite line of charge, but what you can do is that you can take a wire and it can be very close to wire. What do you mean by very close? Much closer to the wire itself than the ends of the wire. Then, for practical purposes, the wire is infinite. Now, what do you do here? Now, this situation, let's say that we're trying to calculate the electric field over here. Okay? This situation possesses a certain symmetry. Now, this is cylindrical symmetry. So they actually call this capital R, meaning that first it has translational symmetry along this line because we assume it's infinite, and second, there's rotational symmetry around this axis, and there are reflectional symmetries. There's the up-down symmetry for any plane that passes through this wire. There's a reflectional symmetry over the plane, and for any plane that's perpendicular to the wire, there's reflectional symmetry for the two sides of that plane. Yeah. And we're not going to utilize all of these, but these are generally the symmetries you have. So as I said, this is called cylindrical symmetry. So it incorporates translational symmetry, rotational symmetry, and these reflectional symmetries. And so the Gaussian surface you need to draw here has to reflect that, right? Once again, at the risk of boring you at this point by repeating this again and again, I want to use Gauss's law, but I don't want to take this integral. I want to simplify the integral in such a way that I don't need to take the integral. So I want to choose a surface where the normal vector is either perpendicular or parallel to the electric field. Now, what would the electric field look like here? So I'm not asking for the magnitude, which is what the question is asking, but what will be its direction? Like, can the electric field be pointing this way? No, that breaks the reflectional symmetry. Can the electric field, if we look at this from one side, let's just draw our wire like this, and the electric field be like this. No, that will again break the reflectional symmetry. Okay, so we went over this last time, that there are certain symmetries. The electric field has to be perpendicular to this wire. Okay? And that suggests that I in fact draw a Gaussian surface that looks like this. Okay, a cylinder. Now, it has to be a closed surface. You can't have just the side of the cylinder. Gauss's law applies to closed surfaces, but this is fine, okay? Because those two sides have a specific interaction with the electric field. So for the curved side of the cylinder, my normal field is going to be, my normal vector is going to be parallel to the electric field. For the two caps on the two sides, okay, so over here and over here, this is going to be perpendicular to the electric field. And this, of course, simplifies things immensely for me. When they're perpendicular, this dot product vanishes. When they're parallel, this dot product becomes a simple product. Okay. So let's, we need to fix the length of the cylinder. Let's call this L. And let's write down this integral and simplify this. Now, here. So I have this integral over the cylinder. This one I just drew. I'm going to divide this into three parts. Okay. Let's call this side 1 and this side 2. So I'll just call this cap 1. So it's no longer a closed surface. Plus cap 2. Plus the side. Right? The argument inside is the same. It's E dot dA. Now, for the cap 1, E dot dA just vanishes. So this integral is in fact 0. For cap 2, the dot product again vanishes, so does the integral. So this is also 0. And I end up with this just side of the cylinder, E dot dA. Okay. Now it's time, E times dA. Now it's time to use the rotational symmetry. Because I have rotational symmetry, and because this cylinder that I have drawn is the same axis as the wire, all the points on the surface on the side is equidistant from the wire. Their distance is the same, which means the magnitude of the electric field should be the same. I don't know what it is, but it has to be the same. Okay, so which means I can take this electric field out. So it's going to be E integral dA side. Now I can take this integral. It's an integral on the surface, the side of the cylinder, but it's just a infinitesimal surface areas. So it's just going to be the area of that side. Okay, and I know what the area of that side is. So if this is distance R, when I open this up, this is going to look like a rectangle. One side of the rectangle is going to be L. The other side of the rectangle is going to be 2 pi capital R. This one is electric field times 2 pi R times L. Okay. Now, at this point, you might be worried. No, L is something I made up. Okay, so my result cannot depend on L. L is the height of this hypothetical Gaussian surface I just drew. If my result depends on this, it just doesn't make sense. It cannot, should not depend on this. Okay, but let's proceed. So what's on the left-hand side? So on the left-hand side is the charge enclosed divided by epsilon naught. What is charge enclosed? What's the charge over here? So I'm just looking at this part, okay? The part of the wire that's inside, that's just enclosed by this cylinder. And what will be the charge over there? So what is the length of the segment that's inside the cylinder? It's the same as the length of the cylinder itself, right? Can everyone see this? So I have a wire. I put a cylindrical surface around it. The part that remains inside the cylinder has the same height as the cylinder itself. I mean, I'm very bad with 3D visualization. If I can see it, you probably can see it too. But if anyone has trouble, we can try to be more elaborate. Okay, so I know the length of this. This is also L. But I also know its charge density. So the charge for that part is the length times density. And as should be, this is now lambda times L by epsilon naught is E 2 pi R times L. The L's just go away. And the electric field is lambda over 2 pi epsilon naught R. A result we already found using Gauss's law. Right? So from a point charge, the electric field strength goes as 1 over R squared. From a line of charge, it goes as 1 over R. From a plane of charge, it goes as, well, it's constant, R to the 0. Okay, now, what if this was a finite rod? Okay, so this wasn't infinite, but it was of finite distance. Now, presumably, I would need to find a different electric field, right? That's what I did when I applied Coulomb's law. This thing here was something more complicated. It wasn't just R; it was like R squared plus this L squared. It depends on the side and how far we are from the sides and so on and so forth. We obtained this result in the limit that our distance to the rod is much larger than our distance to the sides or the length of the rod. Okay, so where would we need to change this? Where would things go wrong? So for a finite rod, this result doesn't hold, which means this argument doesn't hold, so it must be failing somewhere. Where does it fail?
And
At the very beginning.
the rod.
Hmm?
End of the rod, hocam.
No, there is a mistake in this argument. So can I say that this integral is 0, this integral is 0, so I end up with this, and I take E outside, and so on and so forth. Which part of this argument do I need to change? Everything fails, actually. Right? So this is not 0, because the electric field here is not necessarily in the radial direction. Right? The electric field could look like this. It's not going to be perpendicular to the caps. It's not It's not going to be perpendicular to the normal vector at the caps. It's not going to be parallel to the normal vector on the surface, and so on and so forth. Yeah. So this is going to just fail completely. You can't write this. You can't write this. You can't simplify this. And nothing would work. So
Hocam Coulomb law kullanabilirdik değil mi sonra?
we already did actually. Yes, we can use Coulomb's law. We should use Coulomb's law because we don't have any symmetry, and we already did use Coulomb's law. This was one of the examples we saw. So whenever you can't have symmetry, the first thing you check is, can I use superposition somehow? Can this be solved with superposition? There is no symmetry here. Like if this was 2 infinite rods, I would still use Gauss's law because I can use superposition. I can calculate electric field from one infinite rod and then the other infinite rod and add those up vectorially. But if those fail, in this case they would, we just revert to Coulomb's law. And if you solve enough problems, if you make enough exercises, it's going to be clear which is the way to go. Because you're going to develop some intuition. Yeah. At this point, it's hard for me to explain what's going on, but there's a way to get used to this. Okay, so I'll stop here.